On today's laboratory work, I want to show you some physics of magnesium boride, magnesium diboride. Previously, we have worked with magnesium diboride in our 10th laboratory work. I checked it. So in the beginning of the second term, and as you may notice, I choose the materials. So in the logic that we can show some electronic properties, and then we can go further and show some phonons or maybe electron-phonon interactions, interesting things for these materials. It was for titanium selenium 2 when we studied its electronic properties, its charges wave thing, and then we studied this cone anomaly with phonons. And now we are going to magnesium diboride, which is what's how do you think, what's the interesting, why did I choose magnesium diboride to show in this topic? It has very prominent feature, which makes it unique material. It's a superconductor with record critical temperature. With record critical temperature among conventional superconductors. So it's like 39 Kelvin, 39.5, something like this. And it's absolute record. So next record, it's like 23 or something like this. And then we have this high temperature superconductors. So maybe, and also we will discuss some physics, so some hypotheses why it can have so huge critical temperature. I propose now start the calculations, and then we will discuss magnesium diboride, and I will repeat some things about electron-phonon interactions, because I think it's a rather complicated topic, and one time is not enough. So our algorithm, we will start with relaxation, then we will make two sets of self-consistent calculations, one with this Eliashberg function, the spectral function A to F, then phonon and electron-phonon calculations together in one calculation, and then a lot of post-processing. And we'll get this critical temperature for magnesium diboride, and we'll see if it consists with experimental data. I hope you all downloaded lab 18 folder, and we can start from the relaxation. Part. We have already done it in 10th, in the beginning of our semester, in the 10th laboratory work. But now there is something new thing. I will show you, it's better here. Something new is this pseudo potentials. So we use ultrasoft pseudo potentials because only for them we have this pH. So only for them we have this electron-phonon interactions routine. And also we have added cut RHO. It means not only cutting energy for wave functions, but cutting energy for RHO, for electron density, which is like electron function squared.
Well, the question is, if you don't do it explicitly, what is the default value
of cut RHO? 4 times of cut double FC. But these pseudo potentials, they need higher value because they are more complicated. These pseudo potentials, they are more complicated, more advanced than POW pseudo potentials which we used before, plane waves pseudo potentials, and that's why sometimes default cut ratio it's not enough. So we had to make it with 8 or 10 or 12. In normal, we had to make convergence test for cut ratio also.
why don't you put higher or lower threshold forces and
What do you mean a lowered threshold?
Forces threshold after the state or 6.
You mean why here? Yeah, only -4. I tested it. It was okay. So magnesium diboride also has one excellent property that all atoms here they are in their best position. So the forces on them are 0. So that's why 10 -4 is okay because it's 0. So we'll start the calculation. I'm going to lab 18 to the relax folder, and I can just launch calculation. VS script. Maybe we can do it in short queue because now the cluster is slightly overloaded. I'll see how to do it. This short queue. PBS minus Q short. So let's open our script, and then we should add the Q. It will be like PBS minus Q short, and it will go to the short Q because it is not overloaded. Relaxation. Now I'm on the relaxation stage, and you see the forces. Yeah, that's why I choose only 10 in the -4s because forces acting on these atoms are 0. That's very good. So we had only to release the stress from our unit cell, and it will be done very quickly. Yeah, job done. I want to copy. So I want to copy sodium-1 and sodium-3, and that's all because atomic positions didn't change. And I will paste it into SCF. SCF in. I had so this sodium-1, sodium-3, they are from default structure, but they're not ideal. That's why I will remove them. This is input SCF input for spectral function. So it has only this spectral function tag LA2F true. And yeah, and we also use a lot of key points to make the calculation because we need very dense mesh for this spectral function.
What number of key points do you use?
18, yeah, 18. You should have this in your file.
Says the default is not a set, but LBH.
What do you mean, LBH?
The name of the folder, SF.
SF A to H, A to F, A to F. We will do it regular SF after this. So we can do this SF and also regular SF. This SF with this option for spectral function and with increased points. Why we change them? So if we have super cool cluster, we maybe we can not distinguish them. So we can use only one run SCF, but we don't have such cluster. That's why we will use lower number of key points for regular SCF. I also add this short. PBS minus Q short. And then we are going to regular self. Regular self. We should also paste into the input our new lattice values here. Now it's a regular SF, normal SF file. So the difference between them is only the absence here that tag for spectral function and lower number of keypoints. So I use 999 keypoints, and for my tests, which I provided yesterday, it was okay. So 999 was okay. And yeah, it's like 30 seconds for each. Tell me when you will finish SF and we will go to electron-phonon, and then we'll have some discussion about the theory and about magnesium diboride. You should to copy it. You should to copy. I can show you, but normally you had to copy it from output of relaxation. This is a sodium number. You can take it from here. And they should be, so it's important. They should be the same in both SCF runs. If they will not be the same, for example, you will forget to change this SCF, this sodium, yeah, it will be. For SCF, we will always have only one cycle. So we had to copy, you see, we had to copy save folder from SCF, from normal SCF, and also XML file from normal SCF. And XML, and MgB2 XML. What do you mean? QL it's just a log with some information. XML and .save folder. And also from this SCF A to F folder, we had to copy this A to F save. So it's a file which will be used by electron-phonon interactions. So now the calculation started. We have this normal phonon routine, like so we have dynamical matrix 333. Okay, maybe I will start better from this. So here we have this threshold 10 in the minus 12. It worked. It worked for me, and I hope it will work now. Then we have this LDISP to allow these calculations. MS1 and MS2 is the mass of our atoms, and this is our mesh for mesh. So 3, 3, 3. It is not enough for maybe for papers, but it will enough for us, and it will take not so long time. Last time we used 333 mesh for plumbum, for lead, and we had only 4 irreducible points, but now we have 6 irreducible points because we have another symmetry. So it's a hexagonal symmetry, not cubic symmetry like it was for lead. It had to be 3 by 3 by 3, 27 key points, and all these 27 key points, they are here. So they are so each of these key points, it can represent. So I think that first key point represents only itself, but another key points will represent several key points, which was reduced by symmetry to all these irreducible key points. For each key point, we have modes. We have 3 atoms. That's why we have how much modes we have? We have 9 modes for 3 atoms. Because we have 3 acoustic modes. So each atom has 3 degrees of freedom. That's why we have 9 modes, 3 acoustic modes, and 6 optical modes. Yeah, and they will be distributed among representations. So representation this is also some tricky thing for symmetry. So how we can combine them? So you see that it is combined not in the 9 different calculations. It combined into 6. So symmetry reduced by 3 the number of calculations. On the first representation, we have only 1 mode, then we have 2 modes, and so on. And each of this representation is SCF calculation. So this was for our phonon things. This is SCF calculations. Yeah. Here we have the dynamical matrix, which was calculated for our first key point 0, 0, 0. We have this. Here you had to see if we will have negative modes, negative values. If we have not huge negative value, like I don't know, -1 terahertz, it's okay. But if we have huge, maybe something wrong with our calculations. Maybe it's not enough. Maybe we didn't made normal relaxation, or maybe we didn't choose enough number of key points, or so on. Here should be all okay. So here they are all positive. Then starts this electron-phonon part. For electron-phonon part, so this thing is common. This thing is for phonons. It was the same for phonons, and here it is the same. And filled in, it means that we will collect all our dynamical matrices in these files with these names. How many dynamical matrices we will have? You'll have 6 dynamical matrices for 6 irreducible key points. So we have 6 dynamical matrices. And this is electron-phonon part. So it's like where derivatives will be saved, like these derivatives. I don't remember what means trends, but we had to use it. Electron-phonon, we choose the model of electron-phonon calculations. So it means interpolated. It means that we will have some number, we will have some range of broadening. We starting from 0.05 broadening, and we will have 10 steps. Each will be different by this 0.05. And here we work with, so here this broadening starts. You see broadening 0.05 Rydberg, and then it calculates number of dose at Fermi level. Fermi level calculates and calculates this lambda. So lambda parameter is electron-phonon coupling parameter. What's interesting? So what is this lambda? I will repeat slightly the theory from previous seminar. So when electron-phonon interactions are important. So they important when we want to calculate resistivity, and we want to calculate superconductivity, because this conventional superconductivity it rises from electron-phonon interactions. Barden-Cooper-Schiffer theory. One electron interacts with some phonons. This phonons goes to some another electron. It also interacts with it, and they coupled in this Cooper pairs. So and when they are coupling, we have this superconducting gap in density of states. So how that's why it's always interesting to see if near Fermi level we will have this singularities. So this huge peaks. Because in these peaks we have a lot of electrons with the same energy and they are very, very mobile. We have huge mobility for them. In mathematics, first we worked our first term. We worked with only with electrons. So we have here some annihilator and creation, and annihilation operators, some energies like eigenvalues, and here this is part of electrons for Hamiltonian. And for phonons, we have this routine, and we have also worked with them. And now it's some upgrade. We should add electron-phonon calculations, electron-phonon interactions. Here we have electron operators. Here we have phonon operators, A. And here we have some matrix. We need this matrix to, because we have, so we had to take one electron, one phonon, one electron, second phonon, and so on. So we had to calculate some coupling constants between each electrons and each phonons in the system. That's why we will have some matrix elements, and we calculate these matrix elements on this stage. We create this matrix elements. Yeah.
And which file is this that you're showing?
Fedor, one moment. Igor now is asking.
Okay.
Yeah.
Index in some for electrons. Is it the number of bands?
Yeah, it will be the number of bands. So because each energy it's some kind of energy of the bands. Is they also called the Consham states?
Yeah, but well, we can assume that only those bands here.
You mean that we are only interested in this bands near the Fermi level, but our system is bigger than all this Fermi level, so we have to take into account all electrons. Fedor, and your question?
Which file is that that you're showing in the terminal right now?
Now I show you output. It will be MgB2 elf out.
Mm-hmm. Okay.
And I you see I show it with this command. I used this command tail. You see this command tail minus f, and this is the name of file. It means that when the file updating, I will see update immediately on my screen, and it grows and grows. It's useful when we work. You see representation 9, and now it will add some information. It will be also updated here. I can open it regularly. You see, yeah, it was updated, this file. Okay, and now we're calculating this electron-phonon coupling matrix, and this how we will use this matrix. So we will use this in the next way. So we can use now in this matrix of this couplings between electron phonons, we can calculate the spectral function. We can calculate electron-phonon coupling constant. We can calculate electron-phonon line widths, and then using all this information, we can calculate TC. So from this Eliashberg spectral function, we can then calculate this omega in our. It will be like sum of all these specters. Then we had to create lambda, this electron constant, and we have all for critical temperature. So we have we have lambda, we have omega from spectral function, And mu is some constant between like 0.5, 0.15. It's empirical parameter, and we will play with it when we will get this, when we will proceed to this to this step. So we can do it knowing this matrix, and in our calculations, you see this broadening. It is already calculated. It calculates those Fermi energy, and it also calculates this lambda parameter, lambda and gamma. Gamma is broadening, so gamma is here. That's following line width. Yeah, here is gamma, here is lambda. And then we combine them. From gamma, we calculate this spectral function, lambda here, and then we get critical temperature. So it's like Lego constructor for critical temperature. And now, what about magnesium diborite? I think it's rather interesting material. This material has the biggest critical temperature among all conventional superconductors. You see, for simple metals like niobium, record is 9 Kelvin, only 9 Kelvin. For alloys, like niobium, germanium, it's like 23 Kelvin. Organic superconductors, conventional, 12 Kelvin. Molecular superconductors, it's some other thing, like 52 kelvins. And for conventional superconductors, 39 is the record. So for this magnesium B2. Then goes, next step is like 134. It's like high temperature superconductor. So it's another story. For conventional superconductors, which are described by Bardeen-Cooper-Shifter theory, this is absolute recurrence. And the question why? Because, for example, we can take all these diborites, and we see that another diborites, they are not so brilliant, like tantal B2, 9.5 critical temperature. Molybdenum B is also like 6.8. Zirconium B2, 5.5. So it's not like some common feature of this. For example, if we have huge critical temperatures for another diborites, we can say, yeah, something happens with this Bohr, so we can maybe connect it to Bohr. But now it's some kind of only hypothesis why it has so huge critical temperature. We can hypothesize what happens here, and I think you all saw this. I think you all saw this plot because we have built it. I will show you our previous lab. It was in lab 10 when we have built all this. So in lab 10 we have built electronic properties of magnesium B2, and here is it should be somewhere here. Files from our previous lab. Yeah, I hope you remember it. And then also we played with this file. We played with broadening, and I showed you when we increase the broadening, these things are increasing, and at some time it can be like it will be meaningful because it will fill all the space. And now it's magnesium B2. It's band structure, and we see that we have a lot of DOS here. We have a lot of this. We have a lot of states, electronic states, here in this part of electronic density. What is this? What is this part from gamma to A? From gamma to A, if we will go to Fermi surface, we will have such cylinder. You see here in the here near gamma point, this cylinder should be not so wide, but then near near A point, it should be wider, and we see this on our Fermi surface. So we see that here in gamma point, the center, it is not wide, and here it is wide. And then we have such circles around the cylinder. And we can hypothesize that magnesium B2 has two types of electrons, which contributes to conductivity. And I checked some literature that it has two superconductive bands, which created by this sigma and p electrons. And what is this band? So how do you think? What interactions, what bands represents this cylinder? What do you think? Here we have the structure. I mean, what interactions in the structure represents this cylinder? How do you think?
In plane SP hybridized.
Yes, yes. So sigma is in plane hybridized orbitals, and where we have this plane, we have here barite. So this Bohr, it has hexagonal structure. It looks like graphene, yeah. And we have this superconducting sigma electrons here in Bohr, So in the structure, in plane. Why in plane? Because z because z axis in reciprocal space, it represents A and B axis in normal space, because we have this yeah, and that's why so this band, it represents coupling here, electronic states here, and here we have a lot of electrons. They are rather close to Fermi level, and they are rather mobile, these electrons. And then we have p electrons. P electrons, they should connect all these layers, and they are here. They create these bands, this p. Hmm? Yeah, on Fermi surface. So so we have these electrons, yeah, and it creates such circle, and it's like p electrons, p bands, which are rather weak, and they will here it will be z axis, and they will connect these layers. So, and these two types of electrons, they contribute into superconductivity. And what's interesting, that magnesium has almost no role here. So magnesium is like some atom which connects. So we need magnesium to take the structure and to connect these layers of boron, because we have graphite with these layers connected by this weak p bonding, but we don't have boron for this. We don't have like hexagonal boron. And here magnesium, it plays as some intermediate atoms to create this graphite-like boron. And it can be connected in some way to this high mobility of the electron. So it's like so we have huge mobility here in quasi 2D structure, and we have also some mobility, some superconductivity here in this weak p bondings. And if we will it's I think it was like 2015 when 2D boron was created, was synthesized. It was called borophene, like graphene, but borophene. And it was not hexagonal. Borophene, yeah. It was not hexagonal. It was like so it had another structure. So Bohr don't want to create these hexagonal structures unless it is in some unless there are some metal which can connect this layers. Boron nitride, yeah. But only boron we don't have, only boron. what else? So you see how interesting in how interesting things it connects. As for post-processing, if we will return to our algorithm, we will see that we had to, so we finished this phonon spectral calculations and electron-phonon calculations. Now it was finished successfully, I hope. Then we had, but we got all this information in reciprocal space. We got dynamical matrix for phonons in a reciprocal space, and we got this all this this electron-phonon matrix also in reciprocal space. We had to make Fourier transform to get the same things, but in real space, because we are living in the real space. And phonons is some others. There are some real things which it's some oscillations of atoms. So we should take this Q to R step. Then we'll get matrices. We'll get interatomic forces, which we will need to calculate phonon frequencies in real space, and then we will get in real space this matrix, electron-phonon matrix. And then using output of Q to R, we can make two different post-processing things. One is to extract these phonon frequencies into file, which we can then plot. And also we will we will get this gamma sync. So we will get for electron phonon matrix, we will get this gamma sync. I will show you these files. And then we should do the same for phonon dose and spectral functions. Spectral function and phonon dose, they look very, very similar, and they have very close ideas. So phonon dose is like we take from this phonon dispersion, we sum up all the states, and we get this phonon dose. And for this spectral function, we take phonon line bits, these gamma things, and then we sum up them like here and get this spectral function. So it's the same idea as for phonon dose. It's like dose, but for phonon line bits, but not for phonon dispersion. So let's go. We can make this Fourier transformation with this file MgB2 Q2R in. This file, it's very simple. It means that it uses dynamical matrices produced by previous step. Then it means that it's acoustic sum rule. It means that it sum ups how to explain it. So it takes all the frequencies, sum up them, and check if the condition of and check if boundary condition is okay. So if it satisfies boundary conditions. I can show you the formula. Yeah, so it takes all this, for example, charges. It takes all these frequencies. Yeah, and makes its sum to change them slightly to check if the sum will be 0, because our unit cell is neutral. Okay, in other words, we need this thing. Then this is a file which will be created for with force constant FC, force constants for phonons, and this is tag, which is something new for phonon calculations for spectral function. We have another script. The script is LFPP. I made it just for our convenience. It is only in one processor nodes because we don't need more. And here we should change it. Here was lambda. I had to change it to Q to R. Here also should be Q to R. And here should be Q to R. Hmm?
Well, I don't
Uh,
see some laws, but
Yeah. Some of these things may not work good correctly on more cores than one because it's small routines. Usually it takes like few seconds. That's why there was no need to parallelize them. And also I removed from here npool. It was like npool 4. It means it was sync for key points. Now here we don't have key points. That's why it also could cause some errors. So okay, qsub elf. Don't
Wait a second. What should we change in this elf pp?
I will
file?
repeat it. Elf pp. You should change here only this. You see executable. You will see lambda here, but we should change Q to R. And here, everything where you see lambda, you should change to Q to R.
Okay.
Yeah. Sub elf pp. And I think it will take really. Here are all our dynamical matrices of phonons. I think it was successful. Yeah, you see, it takes each key point one. First key point, it stands only for itself. Second key point, it stands for 2 key points. Third key point stands for 6, then for 12. And in total, it will be 27. 3 by 3 by 3. And it was what about dynamical matrices and key points? And here is the thing about broadening. And also here you see the thing FFT check success. That's the thing about this acoustic sum rule. That's Zasser term. It means that when we sum up all these emergent terms, it will be very, very slow, almost zero, and this is what we wanted. Because in other case, we have some distortion to our cell. And it made this for each broadening. And it took only 1/4 of the second. Next step, this matdyn step, matdyn in. In this step, we will extract, we will use as input this force constants file, which was created by Q2R. And from this file, we will create file with frequencies, and then we will plot it. And here is also some path. It's typical. I hope you remember it. It's typical path for hexagonal structures. I also want to change this post-processing file. Here in Q2R, I will change to matdyn. So everywhere I will change to matdyn. Dynamical matrix.
Also the same file as we changed previously.
Yes.
Okay.
We can create each file for each post-processing. Maybe it will be better, but I just changed it. And then I launch it, elf pp. And it will also take like maybe a few seconds. matdyn out. Yeah, we have a really huge file because it takes a lot of information. What we are interested in this file, freak.gp. It means here in this file we have frequencies for phonon dispersion. We have 9 modes, 3 acoustic, 3 and 6 optical. And you see that acoustic modes, it starts from 0 at gamma point 0, 0, 0, 3. And then we have the 6 very huge values, like terahertz, a lot of huge frequencies, they are optical modes. Yeah, and we will build it. We have a script to build it. Script calls MgB2 phonons. It's our common script for phonons, so it's nothing special. And I want to launch the script. To do it, I'm going to interactive mode q sub minus I, and it assigned me on the node. In the node, I am returning to the folder. I had to go to the same folder, lab 18, elf, and here with Python 3.6, I want to launch the script. Phonons. This is to calculate, to make this phonon plots. Phonon plot to check if everything is okay. Yeah, we will make it, but not now. Now we are doing this plot for phonon dispersion. The name of this plot is it's lab 10. I had to go to lab 18, alpha. Where it is? Yes, here it is. Magnesium B2. Yeah, it's slightly ugly. Yeah, you see this fine things. Yeah, but we didn't have more. To make smoother. To make it smoother, we had to increase number of Q points. It will increase calculation time dramatically. We see that everything is okay. The three acoustic models, which goes from gamma point, yeah, they're okay. So we don't have any imagery models. That means that it's dynamically stable, good structure. We have such intensive life of this optical models. See this 800. It means centimeters in the minus first. So we can I will move it to terahertz, it will be like 25 terahertz or something like that. So because
centimeters first is convenient to compare with infrared spectral.
Yeah. If you want terahertz, it will be like 1 terahertz is 33 something centimeter in the minus first. So it will be like 25 terahertz of this thing. So good. It shows us that everything goes well because we got rather reasonable phone. Now I had to return to my to my phone. I had go exit from the node. Exit. Sometimes it don't work from the first time because it says that some works are going on, and that's why you had to type it twice. Also, we have these files, gamma, and this is our gamma. It's like phonon line width. This gamma. I mean, this is this gamma things. We have files for each broadening with this phonon line width. And now we will plot this this spectral function. What I want to do, I want to use this file. This file is like matdyn A to F in, and here it looks like the file for phonon DOS, because as additional thing, it also creates phonon DOS on this grid, but also it creates this function, this spectral function, and here is now nDOS. I propose you to change it nDOS, and I propose you to use 100 nDOS, and then we will change it to 1000, and we will see what will happen. So nDOS, it means number of points at which we will create this spectral function.
Which file is that?
Its file, it calls this is file this matdyn A2F.
Matdyn A2F. Okay.
Its file is for post-processing to create the spectral function. You should change this. And those, it was 1000, then we should change it to 100. And if you do it, you also should change the script, make minor changes. Now here in executable, you do nothing because it's the same matdyn, but here you should change it like to make it A2F. Here should make it A2F. Just name the files. At matdyn, you take it the same. You leave it the same. Yeah. And then I launch it, elf pp. You launch it qe minus script. You can just delete it qdel and it don't have time to rewrite it yet. But if you will do it in 5 minutes, it will rewrite it. qdel and this name of the job. I think those works fine. So let's check this file. We have found those out. We have maybe yeah, we have A2F out. So this like DOS for this spectral function. Yeah. So I think everything is okay. Yeah, 26 seconds. And I want to build it. I also go into interactive mode. I'm returning to the folder. And here I need this file MgB2 A2F Python. It's just file to make this to plot this spectral function. It's almost the same as file for Phonon DOS, so it was like minor changes for it. And I will launch it. Python. So Mikhaila, it was changed or didn't change it? MgB2. Okay, it had to create the file. It had to create plot MgB2 A2F PNG. And let's see. So we have created this plot for, we have created the spectral function for 3 broadening values. So DOS1 is the lowest broadening value. You see it differs a lot. Then 5, it's like 25, 0.25 broadening Rydberg. And this is the biggest broadening. And you see that it converges. So it goes here, and maybe it was not, maybe 10, it was not enough. Maybe we had to take like 20. Because I see that maybe this convergence is not enough, and then we will see it in the we'll see it in our critical temperature. But nevertheless, tenth is better than ones because it goes to some convergence state. the spectral function, and we can measure it. We can measure this spectral function with experiments, so it's very useful to compare with some experimental values.
I've sent the PNG file to your Telegram because I have another picture. Maybe I messed up
Another
something.
picture. I will check it. How might you have almost the same picture but with a lower number of endos. You see, we have in this file we have this parameter endos. Yeah, how much endos do you have?
Oh, maybe I haven't changed. I haven't saved the file. Maybe let me check it.
It's the same, but with a different number. You see,
Mhm.
in your file, it is like it's slightly ugly because it's not enough dots, but it's the same plot. Maybe. You see,
Okay.
I think that something happened, and Feia has Feia the only one who has the right plot for 100 dots, because it is very ugly. Or you also have this ugly. It's almost the same, yeah. 1000 as mine, yeah. Yesterday when I checked these numbers and doses, I got something like Feia for 100, and then for 1000 I got something better. You can now you can Feia you can increase the number of endos to 1000 and relaunch our calculation, and we all do the same. And I see that Igor made it. I also exit from the core because I had to launch ELF PP again, and it will take same time. Maybe it will take a minute because we have a lot of points. I thought that for 100 for 100 dots it will be like this. It will be like left file, but I had it's better. Don't know why. Yeah. I also still waiting. It will take a few minutes. Two broadening values left for me. And you see the size of the file. It was like 18,000. It's like in bytes, 18,000 bytes, and now it's like 10 times, exactly 10 times. Yeah. So we have three files, like the good, the bad, and the ugly. Good, you see, we have these peaks. For 1000, we have these peaks, and it shows that it is very detailed. It's very detailed, and a lot of peaks. So we have say that here we have a lot of the huge phone coupling. Here maybe for this for 100, we don't see the peaks, but it is also rather good. It's smooth, something like this. And this file, which I think it had to be 100, but it's the mystery for me. So I thought this should be 400. But okay, you see how it differs from this file to this file and to this file. And I think that maybe we can increase the number of endos more again, but I don't see now why we had to do it. I think that this 4,000 dots is okay. 5,000 dots is okay. Okay. So and now the last part the last part is to get lambda, to get temperature. I exit from the core, and I will show you this lambda file. MgB2 lambda in. Here it is. So, first line, 3 parameters. Max energy is the energy to which it will make the calculations. Something more than highest Fourier model in terahertz. As I told, 800 SM. So it's approximately 25 terahertz. So I take this 25 terahertz, the Gauss 0.05, and smearing method. It's like Gaussian smearing. Yeah, and then number of Q points. We have 6 Q points. And what this weights? Weight, it means how many Q points represents by this irreducible Q point. Where I can find it everywhere. For example, I can find it in our in output of Q2R. If I will go to output of Q2R, I will see that for first Q point, it's only 1. It represents itself. That's why here will be weight 1. Then second Q point represents 2. Here will be 2. And in the same way, I get 6, 12, and so on. This is just pass to this lambda files. I will show you this path. Elf-dir. And here we have this lambda files. We can check this lambda files. See, it's like for each broadening, it has created the gamma for each broadening. For each key point, we have 6 key points, so we have 6 files. Yeah, and then this mu, and we will change this mu, and we will see the answer. So let's start. I also had to change elf. I had to write here lambda. MgB2 dot lambda in. Elf OP. Here I had to change lambda. You changed QE, yeah? Yes. Okay, so it's already, because it was the last change I made in my testing. That's why we came to it again. This lambda. It will take few seconds, and I had to get the file lambda out. Lambda out. Here it is. And we see our lambda parameters. So what we see here? We see here this lambda, and we see here this omega log, and we see critical temperature. Lambda, omega, and number of doses in Fermi level. And then for each lambda, for each broadening, we can estimate this TC. And we see that it goes for lower broadening. We have rather huge TC, like almost 100 kelvins. And then when it converges, I think it starts to converge maybe, what I mean by converge, I mean that the difference between this and the next will be lower and lower. Yeah, so maybe like this, and this 8 or 9s or 10s broadening goes to converge, and we see this rather good approximation of our TC, of our critical temperature. So it was like 39, and we see this range like maybe 34, 42. So if I don't know the answer, if I don't know the experimental value, I will take some last values, and I will say that it starts to converge. That's why here in this range we should get our answer. So we can 34 and 100. Let's check what will happen if I will change. What will happen if I will change in this lambda in this parameter, Coulomb coefficient? I want to change it to do it like 0.5. And we will see if critical temperature will increase or it will decrease. And I also want to submit it, pp. So let's see. I changed this Coulomb screening 3 times. In 3 times, I made it 3 times lower. And now,
oh, you made it 0.05.
Yes. Its range is like 0.05 or 0.15, something like this. It's not. We can make it very huge. It's an empirical parameter.
0.5.
We can see what will happen. You see, when I made the screen lower, I see bigger TC. So it's like when we have lower when we have too low screen, we have overestimated TC. When we have it bigger, so we have something like near what we want to see.
But don't we have 39? Instead of 39, we got 98 for the highest lambda. Which of these results actually correspond to the real data?
You mean this?
Or the previous one?
In the previous one, it was 34, like 38, 42. We can't say exactly. So we can say the range. So we can say the range of our, because it's this formula. It's in some way it's empirical. It's semi-empirical formula. That's why we should play with this parameter and to say some range of our calculations. It works good with experimentalists. So when for example if we don't sure in some experimental data, we can confirm it. We can say that yeah, this experimental data within the range of our calculation.
So we are looking for critical temperature depending on the coupling constant.
Yes.
Theoretically, if we would have such constants, it is likely that we would get the temperature as seen in this.
Yeah, but you see, here we have also some empirical parameter, and we should play with it in some way. So we don't know it exactly. We know its range, like from some experiments. So what range should be? And we see that on the upper range 0.15, we got rather reasonable TC. But of course, this range of TCs is really huge. You see, 112. 119 and 55. This range is rather huge. Yeah, so we can estimate with it. We can make on the estimations of TC.
For me, it is in the range from 26 to 7 millikelvins.
To 7 millikelvins, because when you make this parameter too huge, it goes down the temperature, and for you it goes down inadequately. So like 7 millikelvins, and for example, if I if I have some had to make some calculations with MgB2, and I don't know experimental data, I will say that it's like from 40 to maybe 55. So it will be my estimation. Then I'll go to the experimental data that it's 39 and say, yeah, you see, it's almost within my range. So my estimation was rather good. Yeah, and we can return to our previous lab. I will show you this. The data for lead. It was Plumbum lead, and now I want to show you the output for lambda. Here it is, lambda, a lot of files. Yeah, you see, you remember last time we worked with lead, with Plumbum, and it was like from 5 to 14. Yeah, it was converged somewhere here, and the real data is like 7 something. Yeah, so it's not like 50 and 119. We have a rather reasonable range for lead, and we have another range for magnesium B2. For bigger clone screen, it is rather reasonable, this range. Yeah, for lower it's like 55, 119, but it's not like 5, 14. So it gives here a rather reasonable range, and it also gives. So from this data, I would say that it's from 5 to 8 or maybe to 9, and experimental data is 7. Yeah, because all this superconductor stuff, it's really rather hard to calculate. It's really hard to calculate exactly what happens here. But we see that approximations they are around our experimental value. So this was what I wanted to show you. Maybe you have questions. If not, so thank you for your attention. Thank you so